Hi, today we're going to be discussing related rates, or we're going to be starting to talk about them. In order to do this, we have to talk about the derivative. Now, we know that if we have a function, let's say y equals, let's say 3x squared plus 4, if we take the derivative with respect to x, we're going to get 6x. And of course, that 4 just becomes 0. Over the last couple of days, we've been discussing something called implicit differentiation. And that is saying, well, how do we take the derivative if we don't necessarily have a function? Something like 3x squared plus 4y cubed plus 3y equals to 7. Let's say we want to take that derivative here. Of course, the first one's pretty simple. That's just a straightforward derivative, 6x plus, but when we get to the 4y cubed, we said we used a chain rule. We said we would get 12y squared, and this becomes dy dx. That's our chain rule. Plus here, 3 dy dx, and that's, of course, just going to equal 0. These dy dx is just our chain rule. And where it kind of comes from is if I have something like, let's say, I wanted the derivative f of x squared. And if I want to take the derivative of this with respect to x, we would get to chain rule f of x times the derivative of the inside f prime of x. And of course, if we just change that f of x to y, we get 2y times dy dx. And remember, and so we can kind of see where that this f prime of x, that this derivative here, comes from our chain rule. Well, today we're going to do something a little bit different. Today we're going to take the derivative with respect to a alternative variable. We're going to take the derivative with respect to t. So, in other words, I want to find dy dt, let's say. And if we look at our original function here, y equals 3x squared plus 4. If I take the derivative of y with respect to t, I get dy dt. Well, now I'm going to take the derivative of x. Because I'm taking the derivative of x, there's my independent variable is t. Because I'm taking the derivative of x, this is going to be very similar to our implicit differentiation. We are going to get 6x, but now we take the derivative of x with respect to t. So it's very much similar to our implicit differentiation because we're taking the derivative with a third variable, an outside variable. In other words, we're making this is very similar to what we did last year in pre-calc called parametrics. And we can do this with all of them. Let's take a look at this one. 3x squared plus 4y cubed plus 3y equals 7. If I take the derivative with respect to t, we're going to get this 6. This becomes 6x dx dt. Plus, this second one becomes 12y squared dy dt plus 3 dy dt equals 0 still because t is my variable here. This is what we call a related rate. And what's really neat about it is, remember, where the function gives us like a position graph, the derivative gives us velocity. So what we're really finding here, when we take the derivative with respect to t, when we take that derivative with respect to t here, we're getting a velocity function. And this is really neat for it and very applicable in a lot of what we do in calculus. Let's take a look at some geometric formulas and how we can use those geometric forms to get the rate of change of area and volume. So here we go. Whoops, hello, wrong button. There we go. So here we have the area of a circle. And I want to take the derivative with respect to time. This is going to give me a velocity. So I'm going to take the derivative of all of them with respect to t. Now be careful, my only variables are a and r. So that's very important. My variables are a and r. So to take the derivative area with respect to t, I get dA dt. And that's going to equal, when you take the derivative of pi r squared here, we're going to drop our 2, and that's going to give us 2 pi. We're still left with that r, but now we have to take the derivative of the inside. This is our chain rule part. We get this dr dt. That dr dt, that's my chain rule. And what this formula tells me, this will give me the change in area, the rate of change of area, which is a volume. So now I can find out, hey, how fast is the area of my circle growing? And we can do for all sorts of them. We have to be careful here. So here we have, for question 2, we have the volume of a cylinder. Now this one's a little bit trickier. We are going to make this a little bit easier in some ways, but be careful. We have R and H this time, and V. So, but here we have a product. So we're going to use our product rule. So to make it easier for myself, I typically keep the pi with the R squared and the H separate. And when I take the derivative, we're going to get dV dt, the first, which is pi R squared. Well, the derivative of H, that's just going to give us dH dt plus H times, be careful, the derivative of pi r squared, that is just 2 pi r dr dt. Remember, so basically it's this. If you take the derivative of a variable, you're just going to multiply by d, the change in r with respect to that variable, or the change in that letter with respect to t. Like h becomes dH dt, r becomes dr dt. Up here we have the Pythagorean theorem. Can't spell theorem, so I'll abbreviate it. When we take the derivative, we're going to get 2a dA dt. We just drop our power, plus 2b, and again, chain rule, dB dt, just like implicit, equal to 2c dC dt. And here they get funner, more fun. This here is the surface area of a cylinder. So notice again, we have a product rule here. And this one's pretty easy, 2 pi r squared, that's just a simple derivative right there. So let's go and take the derivative. The ds dt, let's deal with the product rule. The first 2 pi r times the derivative of h, which is just dH dt. Remember, we're taking the derivative with respect to t now, plus the second h times the derivative of the first 2 pi r, which becomes 2 pi dr dt. Now, why does it become dr dt right there? Remember, my power on r is 1, so r just goes away. We're not done. Plus, now we have the derivative here. This is our product. This is just our power rule. We're going to get 4 pi r, because remember, we're just going to drop our power to the first dr dt, chain rule. And there's your derivative. I think that's probably the worst one there is. Oh, thank goodness. Area of a square. So, ready? dA dt, the change in area with respect to time, is, drop your power, 2s, be careful, chain rule, ds dt. 4 pi r squared, this is the surface area of a sphere. You have nothing to sphere but sphere itself. So taking the derivative, we get ds dt, and that's going to become, drop your power. R is my only variable here, so that becomes 8 pi r dr dt, or as I like to say, dirt it. Here we are for number 7. We have a perimeter of a rectangle. The derivative of p, dp dt, is, well, the derivative of 2l just becomes 2 dl dt plus 2w, 2 dw dt. Volume of a cone. We're gonna learn to love this one, but we actually make it a lot easier for us in the future. Be careful. Notice we have a product rule here. Again, anytime we multiply two different variables together, it's a product rule. So dV dt becomes, ready, the first, I'm going to treat this as a 1/3 r squared. H is my variable here, dH dt. plus the second h times the derivative of the first. That becomes 2/3 r dr dt. Just like implicit differentiation. Well, why don't we do it on the h? Well, that becomes h to the first, so it's just dh dt. H to the 0, I mean. So, very simple. And number 9, this is the volume of a cube. There we go. So v is my variable, dv dt. Be careful, this just becomes 3s squared. Remember, s is my variable. Chain rule, ds dt. Very easy to do these. Yep. Another Pythagorean theorem, or actually an equation of a circle. This is a circle with radius of 5. So take the derivative of x, that becomes just 2x times the dx dt plus, same thing with the y, 2y dy dt, and the derivative of 25 is just 0. Circumference of a circle, this just becomes dc dt, you ready? 2 pi, well, what's the derivative of r? Just dr dt. All right, volume of a sphere, again, you have nothing to sphere but sphere itself. Ready? Here we go. We'll take that derivative. We can get dv dt is, drop your power, this shit becomes 12/3, which is just 4 pi r squared. And then don't forget your chain rule, dr dt. Area of a triangle, we're going to see this one a bit too. Again, we're multiplying b times h, so again, this is our product. So the change in area, dA dt, becomes 1/2 b dh dt plus h times the derivative first, 1/2. The derivative b is just db dt, dibbed it. All right, and there's some other ones too. We can use trigonometry too, like right here, right? If I have a cosine of theta is the opposite over, that's the hypotenuse, right? I can say, therefore, the derivative cosine, be careful, this is a big chain rule, becomes negative sine theta d theta dt. That's a big chain rule right there. And over here we have of course, our quotient rule, low times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And the kids, be careful, that's the opposite. That is not the number 0 there, so be careful. All right. I hope you enjoyed this video. We're going to take a look at some examples here, and I'll see you guys soon.